I would like to take you back in time to the year 1981. I was 10 years old then, and I was very much fascinated by everything that was related to space travel. And in 1981, the first space shuttle was launched. So as a little boy, I was watching the TV screen for hours and hours. Nothing was happening, just this rocket standing there. In the end, due to all the delays, the rocket was launched even after children's bedtime, so I never happened to see the launch live. But the fascination was there. And one of my youngest son, he is now 8 years old, and he is equally fascinated by space travel right now. So this is him with a toy model of the space shuttle in a space museum 2 weeks ago. And it's really interesting. You can read him stories at bedtime about the inner core of rocky planets, and he loves it. If you would ask him why the crust of Mercury is thinner than the crust of the Earth and Mars, he can give you the right answer. Perfectly scientific enthusiasm at this age, I recognize it. Now, this is the present. I was talking about the past, 1981. So at that time, I tried to read everything you could find about the space shuttle, and that was harder at that time than it is today. There was no internet, so I was basically stuck to the newspapers. And one of the stories they told in that newspaper was that the space shuttle had computers inside. 1981, computers, imagine. And these computers, they would vote about the important flight decisions. Computers that could vote. Closer to science fiction you couldn't get at that time. And it was only many years later that I really understood what that voting was about. So I will explain you that story. The space shuttle had 5 computers, 5 identical pieces of hardware. And they worked in groups. The first 4 of them were working together. And they were loaded with the same software to make all the flight decisions. Same hardware, same software. Each of these 4 computers should give you always the same answer. These 4 would give you always the same answer. And that's why they voted. If everybody voted for the same decision, then that decision was accepted. If one of the computers had a different decision than the other 3, that could only mean that there is a hardware failure in that single computer, so it was taken out of the pool for the rest of the flight, and the flight continues with the other 3 voting against each other. So in this way you could afford a few hardware failures throughout the flight, and everything would still be safe and right. That setup couldn't avoid one particular problem though. If there would be a bug in the software that would make the computer crash, they would crash all 4 together. So you lose all 4 of them. And to be prepared for that scenario, there was this 5th computer, same hardware, but loaded with different software. Software that was developed by a completely independent engineering team. There was a Chinese wall between the teams developing the software for the upper part and for the lower part. But software that should perform the same tasks. So this software was tested independently. It should be able to handle the flight as good as the software of the first computer pool. So if the 4 computers would crash due to a bug, the second piece of software could take over. Now, with hindsight, this was, as a child of 10 years old, my first encounter with what software engineers call the verification process or the precision testing process. The answer to the question, are we building the thing right? Are we building our software in a correct way? Does our software perform the task that we expect it to perform? And that's a similar question we can ask in our DFT world. We also are using extensively software, and we expect that this software does the task it is made for. It should solve the Kohn-Sham equations in a mathematically correct way. So we also have to deal with the verification process, with the precision testing process. That's not the only question though. There is a partner question to this. Software engineers are also interested in the validation question, the question of accuracy. Not just are we building the thing right, are we coding our software in the right way, but are we building the right thing? Are we coding the right mathematical equations? Is the thing we are coding something that mimics nature in the case of DFT? So these two questions always come in tandem, and what I want to talk about today is a partial answer to these two questions for the DFT context. So let's focus it a bit more on the type of questions that matter to us. So what would be this validation and verification, this precision and accuracy mean in a DFT context? Take a piece of silicon, diamond crystal structure, and we ask the question, can you predict the lattice parameter of silicon with your DFT codes? Well, if you go to the literature and you select papers that have answered that question, lattice parameter of silicon with the PBE functional as a function of time of publication, then you see this bunch of answers. Don't be disappointed by this. The vertical scale is quite much zoomed out, so these are more or less the same lattice parameters, but there is some spread on the data points nevertheless. That spread, different software giving slightly different answers, that's a manifestation of the precision limitation in our DFT calculations. Ideally, all these points would be on a nice horizontal line, but they aren't. Now, even if all these points would be on a nice horizontal line, would the predicted lattice parameter be the exact lattice parameter of silicon? Probably not, because we are working with the PBE functional and not with the exact exchange correlation functional, so you expect some deviation there. And that deviation between your PBE answer and the exact answer, the one you will find in nature, that's the accuracy. So these two properties, precision and accuracy, in our case always for the PBE functional, that we try now to quantify. And we will start with the accuracy part, so are we building the right thing? Accuracy, that's comparing your calculation with experiment. And that sounds as an easy question, but as soon as you start doing it, you will realize it isn't that easy. Because experiments and calculation, comparing them, that is as comparing apples and oranges. They are very different objects. So let's look at experiments. What is typical for the orange, for experiment? You always do your experiment at a given temperature. It might be a high temperature or a low temperature, but it is some temperature. Some tiny little effects that always are present in nature will be present in your experiment, no way around. So 0-point motion, for instance, will be there in your experiment. And your experiment is always fully relativistic. Of course, it's nature. The apple, on the other hand, the PBE calculations, they are done at 0 Kelvin, not as in your experiment. 0-point motion is usually not there. If you work within the Born-Oppenheimer approximation, no 0-point motion. And relativistic effects, well, you mostly reduce relativistic effects to spin-orbit coupling, and even then you decide whether you switch it on or off. So the apple and the orange are not very equal to each other. So what do you have to do to compare them then on a right basis? And one procedure would be, you take your experimental data as a function of temperature and you extrapolate them to 0 Kelvin. then at least that experimental value is, as far as temperature is concerned, comparable to your DFT calculation. You can make back of the envelope estimations of zero-point effects, zero-point motion effects, and subtract that from your experimental values. So then you have a pseudo-experimental value without zero-point motion, should be better comparable to your DFT calculation. And at the DFT side, well, many codes do not have full relativistic effects, but at least they have spin-orbit coupling. So be sure you switch on spin-orbit coupling as soon as you pass a certain z-value, which we put at lutetium. So if you do these measures at the experimental and the computational sides, you will have lists of data that are mutually comparable. Of course, this assumes that you have many good quality experimental data. And with all these restrictions, these are not too easy to find. So therefore, we try to select a test set of materials that has been often studied in the history of science, so where you can expect to have these good quality experimental data. And this set of crystals are the elemental materials in their ground state. So for the element iron, you take the BCC iron crystal, has been measured by X-ray diffraction at any temperature you can imagine with high precision many times. For magnesium, you take the HCP magnesium crystal, and so on for the shown part of the periodic table. That's a data set you can find even in well-curated lists in textbooks, so you have good experimental data there. So for this list of 71 crystals, you now make your DFT calculations. Find the equilibrium volume, for instance. You do an energy versus volume scan and you determine the equilibrium volume. And on this plot, you see for these 71 crystals, on the horizontal axis, the calculated equilibrium volume. On the vertical axis, the corresponding experimental quantity. If you would do that with the correct exchange correlation functional, then all these data points would be on that faint black line, which is the y equals x line, the 45 degrees line. So experiment and calculation would be exactly identical. But you see that this is not happening. You have these white dots, and in our data set, these are all the crystals where van der Waals interaction plays a role. All the noble gas crystals, all the molecular crystals, the dioxygen crystal, for instance. So van der Waals interaction is important there. That is not captured well by DFT. So here your volume predictions will be quite off. There are mathematical tools that you can use to objectively identify these data points. You remove them then from the set, and you are left with the set of crystals for which PBE should work. And on this one, you can make a linear regression. That's the red dashed line, which almost coincides with the y equals x line, but has a systematic deviation. And if you want, if you insist on being as close to experiment as you can, without being too strict on doing something that is only purely ab initio, you could correct your PBE results for this systematic deviation. Even if you would do that, you will not be guaranteed to find the correct answer, the experimental answer, because these data points still have some scatter around that linear regression line. So, and that's the scatter you cannot get around. That is inevitably there. That's the limitation of your method. So from such an analysis, you can get a systematic deviation for this functional and this property, and a residual scatter. And you see the numbers there for the PBE functional and for the equilibrium volume as property. Once you know that, you can now go back to your experimental colleagues and give them a type of information they like much better than a bare calculation. Let's apply that to a crystal that is not in this data set. So these were the elemental crystals in their ground state. That means the element tin would be in its alpha tin ground state. Let's now take beta tin, different crystal structure. And you do a bare PBE calculation. That would give you 28.37 cubic angstroms per atom. And that is what typically you would give to your experimental colleague. But now we can go further. We see from our data set that tin doesn't belong to one of these class of molecular crystals or van der Waals bond crystals. So we can be sure that PBE should work here. First important piece of information. Then we know the systematic deviation of 3.8%. So you can correct your bare PBE value for that one. That's not ab initio, I know. But the task we try to perform here is being as close as possible to experiment, whatever are the tools we need to use for that. So that value should already be closer to experiment. That value doesn't have 0-point effects, but we have our back of the envelope estimates for 0-point effects. So we can add that with numbers that are dedicated for this particular crystal. So that value there should be corrected to a large amount for 0-point effects. And then there is this non-systematic error, this scattering of 1.1 cubic angstrom per atoms, and that we add now as an error bar. So the number you would give to your experimental colleagues is not 28.37, but 27.4 with an error bar of 1.1. And that number guarantees you that the value in nature would be in, well, 67% of the cases within that range. And although that looks a little bit more ugly than just the bare PBE value, that is information that is actually much more useful for your experimental colleague. And they will like that. They know error bars. They are experimentalists. So they will like a calculated value with an error bar. If you would compare this in this case, well, we know the experimental result. We have beta tin experiments extrapolated down to 0 Kelvin. And you see that the number is not very close, but it is within this 1.1 cubic angstrom per atom error bar. So this is a way how you can deal with accuracy of a given functional for a given property in PBE, in DFT. You have to go through this whole process of making that linear regression, but once you have done it, your results are transferable to other crystals as well. And we have done this not just for the equilibrium volume, also for other properties you can extract from an energy versus volume relationship, the cohesive energy, the bulk modulus, and the pressure derivative of the bulk modulus. In all cases, you have this systematic deviation and the residual error bar. That was published in 2014. Afterwards, we have repeated this process for other properties. So this is an example from 2016 where surface properties, the surface energy and the work function were calculated with PBE and LDA for a set of reliable surface experiments, and always the same properties, systematic deviation and residual error bar, were extracted. And you can see, for instance, for this work functions, in this residual error bar is 1.3 EV, which means there is no information available so far to verify whether your work function experiment and your PBE calculation for the work function agree with each other within 1.3 EV. So the error bar is huge there. It makes no sense to discuss differences that are smaller than that value. And it's useful to know that. We have applied it also to thermal properties. So this is an example where ab initio ways and semi-ab initio ways were used to calculate melting temperatures of crystals. And again, you have this, this systematic deviation. So ab initio molecular dynamics would give you an uncertainty of somewhat less than 60 Kelvin on your melting temperature. If you use easy estimation formula, where you can guess a melting temperature based on the bulk modulus, the error bar would be 10 times as large. So it's a way to quantify how accurate a given method is for a given property, whether it is a fully ab initio method or a method that includes some empirical formula or empirical parameters. That was about the accuracy part, the validation question. Now we move to the partner question, the precision, the verification. And on our scheme, on our graph for silicon, that means we are now not dealing any longer with the deviation from experiment. We are looking only at calculated results, and we try to estimate how close they should be with respect to each other. Now, as you can see from this artistic impression made by Kurt Leagre about DFT codes, we have a lot of DFT codes and related ones on the market. And the question is, how can we quantify how well these codes do agree or do not agree with each other? You can spend 5 minutes to this picture and try to find where is your favorite code. The question we will ask to these DFT codes is very much the same question that was asked to the computers in the space shuttle. You give the same task to 2 codes, you get their answers, and you compare to which extent the answers are comparable to each other. In this case, the 2 calculators should hopefully give you the same answer too. We will use again a similar test set, these 71 elemental crystals, with a few modifications. So we do not insist now on the ground state for every crystal, for every element, but we take something that looks like the ground state and is as easy as possible. For instance, the sulfur crystal, the ground state there, experimentally has many, many atoms. We take another crystal that has nearly the same bond lengths, but that has only 2 or 3 atoms in the unit cell. Just to speed up your calculation time, you are comparing code against code and not comparing with respect to experiments. So the exact crystal structure does not matter too much. So we have 71 easy crystals for which we do DFT calculations according to a given protocol. So for every crystal there is a predefined set of 7 volumes for which both codes calculate the energy at that pre-described volume. You then make an energy versus volume fit with a Birch-Murdigan equation of state, and it's this Birch-Murdigan equation of state for that crystal with 1 code that you are going to compare to the same result for another code. In which way do you compare it? Not by looking at the fit parameters, but by looking at the entire curves themselves, because there you have the full information. So you take the 2 energy versus volume curves, you align them such that the minima coincide, and then you overlap the 2 curves and you look for the area between them. If both curves would predict exactly this, if both codes would predict exactly the same energy versus volume curve, these 2 lines would coincide and the area in between would be 0. If there is a deviation of whatever kind, then the area will be different from 0. And that is expressed by this quantity delta, which is a measure for this area between the curves. Let me apply that to a specific example. I take the FCC copper crystal and I do these calculations with the Wien2K code and with the VASP code. You get 2 curves that are to the naked eye almost indistinguishable, and if you go through that procedure you find that this delta value for FCC copper is 0.8 millielectron volts per atom. These kind of numbers probably don't tell you much, but you will see them appearing quite regularly. And keep in mind that everything that is below 1 or 2 millielectron volt per atom means in practice this is undistinguishable. These are two answers that are, for all practical purposes, identical. So Wien2K and VASP agree very well for the FCC copper crystal. You don't do this only for FCC copper, you do this for all 71 elements of this test set. So you see on this graph the numbers, the delta values for all these easy crystals, and you can make an average of this entire set and conclude that on average the difference between Wien2K and VASP is 0.3 millielectron volt per atom, which means these two codes give you identical results. This was done not only for Wien2K and VASP, this was done for a long list of different codes and various flavors of different codes. And you can put all these codes on one axis and the same codes on the other axis and calculate the delta of every code with every other code. Then you get this big matrix. Don't look at the numbers, just look at the colors. If something is green or greenish yellow, then it means a delta that is below this 1 or 2 millielectron volt per atom threshold. So all these green and yellow codes are agreeing very well with each other. If the deviations are larger, I read here from nearby that there is something like 6.4, 6.7, that is this slide red. That means a code that is deviating quite a bit. Let's zoom in on this table, and I take only the upper left corner. So back to this graph, it's here the upper left corner, where we take the all-electron codes, the ones that mathematically have or numerically have the least amount of approximations, and we compare the all-electron codes with the other all-electron codes. So an internal all-electron code comparison. And now you can read the numbers, and you see that everything here is even not exceeding this 1 millielectron volt per atom. So the values here are averages over the preceding row. So all electron codes are in excellent agreement with each other, which is a good reassurance for our community. It doesn't matter which all electron code you take. If you handle it well, you will get the same predictions. To connect these delta values to numbers you are more familiar with, what does a deviation of 1 millielectron volt per atom mean? Well, in terms of lattice parameters for a typical situation, it's 1/100th of an angstrom. For a bulk modulus, it's 1 gigapascal. So if you take two DFT predictions for the same crystal by two different codes, and they agree on the bulk modulus by less than 1 gigapascal, you can be sure that there is no reason to worry about. If they would disagree with 5 gigapascal, then maybe one code or both codes together are not operated in really the way it should be. Then you can hunt to bring them closer together. So this was all electron codes, but you can tell the same story, for instance, for the ultrasoft pseudopotentials. So here now the ultrasoft pseudopotentials are compared to the all electron codes, and you see again the same level of deviation. That's quite surprising. You would assume an ultrasoft pseudopotential that involves quite a dramatic operation. You have to make a scheme to produce a pseudopotential that behaves in many respects as good as the exact potential. Don't you make approximations there? Well, from these numbers you see that people who have developed these pseudopotentials can do that in such a way that the deviation from an all-electron code is negligible. Except if you go for somewhat older sets of pseudopotentials, this Vanderbilt number 2 scheme in the DACAPA code, that gives you meaningful deviations, but that is a tool that is old anyway, that nobody is actively using at this time. You can even inspect for codes that have a historical record of pseudopotential schemes, how they perform over time. And that's an interesting table too. Take here, for instance, the CASTEP code, where we have a set of pseudopotentials from 98, from 2013, 2015. and you see how the delta value decreases, and that is really the quality control of these pseudopotential developers at work. They didn't use this delta scheme to produce their pseudopotentials, but they had their own assessments to be sure, to guarantee that their pseudopotentials become better and better. And with hindsight, if you apply this delta test on it, you see that it did work. Their pseudopotential libraries became better and better. And it's not only so for CASTEP, it's the same for the VASP code and for every code for which we have such a historical record. So all codes were really evolving to producing the same answers, and the point in time where they reached this is about, well, 1-2 years ago. So we reached, as a DFT community, the point where we can say the basic tools of our field, wherever they were developed, agree with each other. So if we now would put these error bars on the graph for the silicon crystal, that would be the error bar as you see it here. So all scatter in the lattice parameter within these lines is due to these remaining imperfections in the codes. So this amount of scatter is not something you have to worry about. Only if you would exceed that value, that error bar for silicon, you might hunt for a user error somewhere in your calculation. I constantly said we, but I didn't mention who are these we, who are the people who did all these tests. And as you can see from the author list of this paper, this was quite a large group. So the idea was here, nobody is able to use all these codes in the expert way. So to avoid human errors, we try to find for every code the expert users or even the developers of that code, and they should run the calculations for their code to make sure that the code was really handled in the way it should be. And then you put all these results together and you get that big matrix. The interesting thing is, because this is a subset of the entire DFT community, wherever you go, there are people who are in this list. So I made the exercise yesterday evening. If I take the list of speakers of this workshop and I compare it with this list here, then I had 1, 2, 3, 4, 5 people who match. So if you have questions about code-specific issues for this story, you can, during this school, approach certainly these people. Is anybody of them present in the room? Yeah, Volker, okay, I knew this before. Nobody else, but either you met them the days before or you will see them in the next days. And also useful to notice, this was a kind of project that 20 years ago wouldn't have been possible, because with so many people, you need to communicate a lot, and without email or social media, you don't have the tools to communicate. So 20 years ago, writing letters or sending faxes, that would have been impossible. That also implies that these 69 people never all together met. So this is the largest picture we could gather. This was at the Psyche conference in 2015, where we had in the same room about 20 of these 69 people. There were other people of the group present at the conference as well, but not in the same room. So this is the highest number we could ever reach. Okay, we dealt with validation, accuracy, comparing to experiments. We dealt with verification, precision, comparing codes to each other. All of this was the past. What are the ongoing things? And I will not be able to tell you definite conclusions here, just give you a flavor in the direction we are thinking right now. And this direction is meant to counter some criticism that you can express to this test set we have been using so far, the 71 elemental crystals. You can say, well, this test set is too small. If you want to extract conclusions that are valid for every solid you can imagine, then 71 elementary crystals is probably too small a subset to base your conclusions on. So let's try to increase the test set in a way that it is more structurally diverse and more chemically diverse. You could also complain that the test set does not contain all elements of the periodic table. There are not all the lanthanides are in there. There is lanthanum, there is lutetium, and you hope that everything in between behaves in the same way, but maybe that is not the case, so you want to have europium, it's not in the test set. So let's increase the test set such that it really includes all elements. And even after our cleaning between the test set used for the accuracy and the test set used for the precision, there were still crystals that take a little bit more time than you would like to. So let's really emphasize now that all the crystals that are in the new test set are really fast, hoping that we can develop in such a way a test that the code developer can run overnight, every day, to verify whether there have no bugs been introduced into the code. That would be a nice goal to set. So can we make a test set that meets all these criteria? Well, our attempt, and there are certainly many more ways to have a test set that has these properties, but our attempt to meet this is to have a test set that contains for all elements from Z1 to Z95, without exceptions, without gaps, make the FCC crystal for that element, the BCC crystal, the simple cubic one, and the diamond crystal. And then you have all coordination numbers from 12 to 4, so you have quite a good sample of structural diversity. That would be one part of your test set. Still a bit biased on the elemental crystals, but at least it is now more structurally diverse. The second part would be a set where we take for every element X, or for every relevant element X, these 6 oxides. And under each of these oxides there is a crystal structure that is chosen to be as simple as possible, has only 1 degree of freedom, the volume. And in this way you cover all the oxidation states from 1 to 6 for that element. So this is chemically diverse. And it's not an elemental crystal anymore. It's an oxide. Still we have some bias, we have elemental crystals, we have oxides. A third part where we try then to be as realistic as possible for experiment is take for every of these 95 elements in a hand-picked way, so you select it yourself, 1 binary semiconductor with a simple crystal structure, 1 binary metal with a simple crystal structure, 1 binary ionic compound, 1 binary covalent compound, and in this way you will have about, if you choose this in a clever way, about 400, 500 simple crystals that cover all these different types of chemical binding. And these should be crystals that exist in nature so that you have some connection to experiments. If you take all of these 3 parts together, then you have a test set that is about 1200 crystals that all are easy and that is certainly not too small anymore, that covers all elements and that is chemically and structurally diverse. I think such a set would be the minimal set that covers structural and chemical diversity in a somewhat balanced way. In other words, you could say this is the minimal set that you should test a pseudopotential to or a pseudopotential library to verify that it really has the same performance as an all-electron calculation. So one of the things we are working on is producing all-electron calculations for that set such that pseudopotential developers have something to compare their pseudopotentials to. And I can show you a few first results. We didn't advance too much yet in this direction, but some things are done. And the example is for it's again a Wien-VASP comparison, now with what is called in VASP language the GW-ready PAW projector set. And the overall delta for this set with Wien2K was 0.3 millielectron volts per atom. We will focus on one element, antimony, that had a delta value of 0.2, so it's representative for the entire set. And for antimony, we will go through these oxide lists. So we take the 6 different oxides ordered from oxidation state +1 for antimony to oxidation state +6, and we calculate the delta between VASP and Wien2K. And we find it's quite a bit higher than this 0.2 for the elemental antimony. It's in the range of, say, 4. Now, this was done with VASP projectors where you have 5 valence electrons, which is the default for that particular VASP projector set, while in Wien2K we took its own default where we have 21 valence electrons. So maybe that's the reason for this larger delta value. So let's play with this. We take now the 4p electrons for Wien2K in the core. So we have only 15 valence electrons here and 5 there. The delta values even increase. Could be. These are still not the same sets of valence electrons. So let's add now in VASP the 5d electrons to the valence. We take a different PAW projector set and we get this. The numbers go down a little bit, but they do not reach that 0 point something level. Although now the number of valence electrons is exactly the same. So this should be the most fair comparison you can make. Interestingly, if you now go back here to the default situation in Wien where the 4p electrons are valence electrons, then the numbers in 5 of the 6 cases become very small. And if you now look back to the original tests with the elemental crystals, this 0.2 was obtained in exactly this configuration. So it isn't the most fair comparison you can make. The number of valence electrons is not consistent in both cases, yet it gives you the best agreement between the two quotes. So I don't make any conclusion here, but there is something to think about. And this kind of analysis you can do now not only for antimony, but we hope to do it in the coming year for the entire periodic table, also for the elemental crystals with all the structural diversity. So we hope to learn much more here about the reasons why codes do agree or do not agree at this very high precision level. That concludes the scientific part of this presentation. I have 2-3 minutes left on a different aspect, on teaching. Traditionally, when we teach whatever topic, when we teach science, when we teach DFT, it happens in this kind of settings, a setting that is very comparable with what we have here today, a speaker in front of an audience. There are good reasons why it happens that way. We can discuss about that later. But it's a situation that is a reminder of the past. This is how it was done 1,000 years ago, 2,000 years ago. We can wonder, should we do it still in the same way today? And there are indications that we are not always doing it anymore in the same way. You see that camera there. This lecture is being recorded. It will be set online. Other people can watch it. And I can predict that in 2-3 years from now, many more people will have watched it online than the 30-40 people who are here in this room. So what we are doing here is valid for you, is relevant for you, but it's almost only an excuse to make a recording that will be valuable for many more people than the ones that are here. And you can extrapolate that thinking and say, why shouldn't that become the default way of teaching? So at Ghent University, we have been experimenting with such schemes. How can we break out of the walls of our lecture rooms and make the teaching available for many more people? And one of the things I have been playing with in the past 3 years is by making recordings of my DFT classes and putting these online as pre-recorded video lectures together with a set of tasks. So now I ask my students for this week, watch these videos, work on these tasks, send me the results one day before our single remaining class lecture. I look at the results, I will give feedback to your work in the class session. So there is no teaching anymore in class, there is just feedback in class. And that's for many students the first time they get feedback, because previously there was no time for feedback, you had to lecture in class. But nowadays, should we always lecture in class? I'm not convinced. So, and once you do it that way, why can't other people watch these pre-recorded lectures? Why does a student still has to be in Ghent University to take a course at Ghent University? They can email the results just as the Ghent students do, and I can give feedback in the same way as I do to the Ghent students if I make a recording of that class session and put that online again, or if I live stream it, as we did last year. Everybody can follow the course. So in this way, we try to expand this course, which was once meant for 10, 15 local students, to a global course that anybody can take. And so there is a website for this course, compmatphys, computationalmaterialsphysics.org. The course is scheduled in our fall term, so it starts at the end of September. If you know people who are interested in this, tell them to go to that website and they can sign up to receive information if they click on that button. It's a very basic course. It's meant for material scientists or physicists who did not have any deep basics in condensed matter theory or mathematical physics. So it teaches somebody the concepts of DFT, and it teaches people how to do basic things with the DFT code, how to read and understand what is written in DFT papers, but it is not very advanced theory. So probably for most of the people here, it will not be the right course, but if you have colleagues who need a basic introduction, you might give them this information. Last year, so we didn't make too much advertisements for this because the course is still growing and developing, but last year we reached in this way an audience that was quite well spread over the planet, and I think it's surely possible with that kind of courses to gather an audience of say 1,000 people per year and teach to all of them at the same quality as if you were teaching to the 10, 15 people in your own class. That's it. I should certainly mention the team at Ghent University who is working on this delta work and many other things. So we have Sam de Wale and Kurt Le Jager, Michael Sluits, Jan Jaken, Merlijn Mertens, and a student from Antwerp, Annelinde Strobbe, who did I don't remember the English word, who did some small student project, but that was very much related to this antimony data that you saw. These were her calculations. Okay, so I leave you with these links. You have at the bottom the websites where we collect all these delta comparisons. So even if after the publication of the work people submit new data sets, they are added to this web page, and you can make, it's a dynamic page, so you can make all kinds of mutual comparisons that you want. The papers that I have mentioned in this talk, you have the links there. You have the link to the course, and I will probably put this talk on my YouTube channel. If you want to see similar talks or talks about other topics from me, you can go there and watch them again. And with this, I'm ready to take your questions.